In our previous videos, we introduced the idea of potential energies and the two types of potential energies we're going to focus on most in this class. The elastic potential energy, that's energy that's stored in stretched or compressed springs and elastics, and gravitational potential energy, the energy that's stored in sort of an object's height. And the fact that if you release an object and it changes its height, that potential energy associated with its height can be converted into kinetic energy or other forms of energy. What we're going to do today is we're going to start to look at what are called potential energy diagrams. And it's a great way of visualizing potential energies. And it turns out you can get quite a lot of information about a system off that, including forces, kinetic energies, and lots of different things. So that's what we're going to look at today. And then we're going to finish up with a short discussion on the concept of conservative and non-conservative forces and sort of summarize our whole energy model to date. So what are potential energy diagrams or energy diagrams? If we think about the potential energies we've discussed so far, we have gravitational potential energy, which is just mgy, mg times height. And we have our elastic potential energy or our spring potential energy, which was 1/2 k times delta x squared, however far that spring is stretched or compressed. And one thing we notice about these, and we'll notice, and it turns out to be true for all potential energies, is potential energies are typically or only a function of position. So that gives us a really nice way of plotting these, right? If you have a function of a variable, you can plot that function as a, as it's dependent on that variable. So if we take our potential energy and we plot it, and let's look at gravitational potential energy for an example. If we plot that potential energy as a function of height, what do we get? Well, we see here we have our variable y, and it's just a straight line with slope mg. So we're going to have something that looks like this, and that's our potential energy due to gravity, and it's mg times y. Now, that's all well and good. We can, we could then pull off this plot if we were given some height. We could immediately pull off a change in energy, but we can actually get a lot more from this, right? If we consider our system as a whole and energy is conserved, we're going to have some constant total energy, right? So imagine I took a ball and I brought it up to some height, y a, we'll call it. I know immediately my gravitational potential energy is whatever that height is. And since I say released it from rest, it's not moving. So that's the total energy. I know the total energy of that system. That ball's going to fall down. The height's going to change. And at any other height, we'll call it YB, I can again pull off the potential energy at that point B. But since the total energy is equal to potential energy plus kinetic energy, I also know that this difference right from here to here is the kinetic energy, right? So immediately off this plot, I can take, if I know the total energy and I know the functional form of my potential energy, I can also figure out the kinetic energy, and we can visualize all of these things. Another thing we're able to do with this sort of thing is if we think back to how we defined our potential energies. Remember, it was the change in potential energy was negative the work done by that force of the interaction in our system. And we know that work was just sort of the force dotted with our displacement, in this case, delta y. So we have the change in potential energy is equal to the force dotted with delta y. We can rearrange that and see that that force is equal to negative delta y over delta u rather over delta y. And if we take the limit as delta y goes to 0, this ends up being the force is equal to the derivative of the potential energy with respect to that position, in this case, y. Sorry, the negative of that. So we know from calculus that this derivative is the slope. So the force that's associated with that conservative or with that potential energy is the negative slope of this graph. And we can see that in this example, right? The slope of this potential energy is mg, and we know that the force of gravity is equal to mg in the negative y direction. So the slope from our plot, mg, throw in the negative because we have a negative sign in the way we just did, and the force can be related to the potential energy in that way right here. So I'll write it again. Force is equal to negative the derivative of the potential energy with respect to position. So I'll write R so it's more general for other things. But again, we can get a lot from these types of potential energies, and they're extremely useful. If we go back to our potential energy on a spring, if you recall, we have the potential energy on a spring was equal to 1/2 k delta x squared, and if we define x of 0 as being our equilibrium point, we have this is a parabolic function with respect to position. So we get something that looks like this, where we have this parabolic potential energy 1/2 kx squared. If we were to take a mass, attach it to the end of the spring, pull it to the right, and then let it go, it's going to bounce back and forth. The spring's going to pull it back towards its equilibrium. It'll overshoot, go to some distance on the left, bounce back to the right, and it'll go back and forth like this. And we can see all of that in this energy diagram. We have our parabolic potential energy. It's described by that 1/2 kx squared. When I pull it to the right, I've given this system some potential energy and it's at rest. So that defines my total energy, that constant. And when I let it go, that's going to, so we can also keep track of the energies in these bar graph sort of charts, where at the start, I've got all the energy in this potential energy of the spring at point A. I let it go. That object, that mass starts moving to the left with some speed. So it goes down to a lower potential energy, but now it has this large kinetic energy here. If so I've got more kinetic energy, less potential energy. My total energy of the system is the same, and it moves back, gets to equilibrium of the spring, but now all its energy is still in the system, but it's in kinetic energy. And the potential energy is 0. I'm at the bottom of this parabola, and it keeps going to the left, and it starts slowing down and getting potential energy, and you can see it's going back and forth. And we have that same sort of thing we were discussing before, where we can get a lot of information from this plot. To give you an idea of more of the information, we can sit here and think of, okay, when is this mass, how far is this mass actually going to go before it stops and starts coming the other way? Well, when we think about that, when it stops, it's going to have 0 kinetic energy. It's going to have stopped. And all that energy is going to be in potential energy, which is defined in this plot as that point where they meet, right? Right here, when it gets all the way over to XL, all of that energy is in the potential energy. This potential energy plot intersects this total energy plot, and that defines sort of our turning point. So we know that this mass is going to go back and forth between XL and XR, those 2 points that it intersects, right? Just like we did, I'll use this one over here so there's more room. Just like we did previously, we can determine the force at any given point. Remember, the force was equal to negative du dx in this case, the derivative with respect to position, or the slope of this plot. And we can see that this is a negative slope. So when I take into account the negative sign in this equation, it's applying a force to the right, and it's pushing it to the right, just like we would expect if this mass was at some position to the left of equilibrium, it'd be pushed to the right. Knowing this functional form of our potential energy, I can take that derivative, the 2 comes down, du dx ends up being kx, and that force is then the negative of that derivative, so it's negative kx, and I recover Hooke's law that we had for force on a spring, so I get that force as well. All of this leads to the concept of equilibrium. When we're in equilibrium, forces are balanced. And we can identify equilibrium points on this plot by saying where, essentially, where are the forces zero? And that's when this slope is equal to zero, or we're at the bottom of this, potential energy diagram. So if we were to have been sitting there with no kinetic energy, we would stay there. Um, so we can get a lot of information from these things. I like to just think of them as sort of, stuff rolls downhill. If I'm at a higher point on a potential energy plot, say I'm, the object's here, it's going to have a tendency to want to go downhill because that slope's negative. The force would be pushing it that way. If I were over here, the slope's positive, so the force would be putting it that way. Forces are going to try and drive it to these minimum in the potential energy diagram. There are lots of examples that you can use this. Not, most of the students in this course actually aren't going to be physics majors, but a lot of you are maybe chemistry or biochem majors or different things like that. You can understand a lot of systems really well qualitatively from these sorts of diagrams. One of my favorite systems to think about in terms of energy diagrams is just two atoms that are bonded together, right? And they're going to have some attractive force that's holding them together in the bond. And it turns out that you can plot that potential energy as a function of separation between those two objects. We'll call that R. So the potential energy of some chemical bond R is going to look something like this, where we have sort of a steep slope like this, and then it tapers out like that as we go to larger R. And it turns out you can get a lot of information just from this plot. So one of the first things we can see is, let's say this molecule is at in a bath. It's got some given temperature that's described by, we'll say, a total energy here that's related to temperature. So we can come across like this, and that's the total energy in our system. We know that that if that's the total energy, that molecule or whatever, the separation between these things is going to oscillate between those two turning points there. So it's going to go to some R minimum, call that R min, to R max here. And it's going to just go from here, where it's all potential energy, back down up here to where it's at maximum the maximum position, where all the energy is back in potential energy. In here, it's going to have some kinetic energy described by, just visualized by the distance between the total energy and this potential energy diagram. We also know that at this, point here, we'll call it R naught, that's where the bond's in equilibrium. That's sort of a way of thinking about the equilibrium bond length. So we, as the atoms get closer together, we've got a slope, a steep negative slope, that it means the force is going to be in that direction, pushing them apart. And it turns out this comes from sort of the nuclear repulsion and some Pauli exclusion and different things like that. But those two atoms, if you push them too close together, they start to push apart really hard. But over here, where they're further separated, you have this electrostatic force between the electrons that are pulling them together that way. And it's just going to oscillate back and forth. So that's all well and good. We pulled off some information, but you can even get more. If we heat up the system, and let's say we go to a higher temperature, we'll call this E2, and now that's our total energy in the system. Well, what's going to happen? Our turning points have now moved, right? R min has come to over here, and R max has moved to over here. So it's going to, the atoms, the bonds are going to shake harder and harder and a bit larger and larger. But one thing you'll notice is, because, this side of our potential energy diagram is really steep and this side's not as steep, it's a little shallower, the R min moved in just slightly and the R max moved out a bit more. So what that means is, if my molecule, if my atoms going between, or my molecule rather, is bouncing back and forth between these two positions and going back and forth, the average position, or the average bond length, I should say, is slowly shifting to the right as this energy goes up. So we've just, in this one diagram, sort of seen how thermal expansion is going to work. You have the average bond length is moving to the right and getting larger as the total energy in the system increases. And we can take that to an even more extreme. If we take the total energy up to, say, here at E3, what's going to happen, right? If that's my total energy, well, I've essentially just broken the bond. If the distance comes this way, it's going to get pushed that way. The system's going to go down to this low potential energy, come out here, but it's not going to have some turning point on this side of the diagram because the energy's too high. It's got enough kinetic energy that the separation is going to go over that hill, and we've described how this bond breaks. When you heat up things, you overcome the bonds and they break. So again, this is just a really quick sort of discussion, but hopefully you can sort of see how all of the concepts of energy and the things we're learning in this class are actually can be really useful in other classes and in your other science courses. This one in particular, just like a chemistry, biochemistry type application. But again, all we're looking at is potential energy as a function of position and sort of relating that to what we know with our energy model. The slope of that's going to be the forces, the total energies, that potential energy plus kinetic energy, and things like that. And by thinking really hard about that energy diagram, you can learn a lot about that system. So the switching gears now from potential energy diagrams, what we're going to do is discuss the difference between conservative and non-conservative forces, and then sort of summarize our whole energy model. So having defined potential energies and how useful they can be, a natural question that might come up is, why is there a potential energy for gravity, but not one for tension or friction? I mean, potential energies were useful. They kind of helped make some of our thinking about energies easier. Why can't we just do it for all forces? And it turns out the answer is that only conservative forces can have potential energies associated with them, right? Which naturally brings up the next question of what the heck is a conservative force, right? How can we identify which forces can have potential energies and which can't? And the sort of standard way that I would define a conservative force is a conservative force is a force that can have a potential energy associated with it. Clearly, this is circular, right? That's not the formal way you can tell, but really that's what it boils down to. They're called conservative forces because they have potential energies associated with them, and thus you can think of that system as having a total energy potential plus kinetic, and that's conserved, hence conservative forces. More formally, though, if you want to know whether forces are conservative or not, they have to meet two requirements. And the math to show these is beyond the scope of this course. But the idea is that the force has to be only a function of position. So it can only be a function of position or a constant. It can't depend on velocity or anything else, right? It has to be a function of just position. So you can see, gravity only depended on y, the position of that object. The spring force, Hooke's law, only depended on the position of the spring, how stretched or compressed it was. Those were two forces, only depended on position. We were able to assign um, potential energies with them. So that's the first condition. The second condition is that it has to be path independent. Uh, right? And what that means is the work done by that force going between point A and point B has to be the same no matter which path you take from point A to point B, right? So if we think of, we have some object here at point A and we move it to point B and we consider some force acting on it, if going along path 1 gives me a different amount of work than going along path 2 when I go from A to B, I can't assign a potential energy to that. If you think about it, our potential energy, remember, is a function of position, and we want to be able to assign a single value at B. But we defined the change in potential energy as negative the work done when going from our initial point A to our final point B. If I go along this path, I'm going to have a different change in potential energy when I get to B than if I went along path 2. If those two, the amount of work is done, I can't define a single change in potential energy, and it kind of throws away how the point of doing all of this. To give you an example of what a force that is path independent is friction. So friction doesn't really depend on position or anything, right? It's just, if we think of kinetic friction, it's just mu k times the normal force. Um, but if we think of the work done, if I go along path 1 here, that work done is just going to be that force of friction along this path. The force is always going to be opposite the direction it's going. So it's essentially the magnitude of the force times the distance that particle would travel along this path. If I take a different path that's a different length, I'm going to do more work. That friction is going to be applied over a larger distance. It's going to do more work. So clearly, for the case of something like friction, that's path dependent. Which path I take matters for how much work I'm doing. The same thing could be for tension. If I applied a constant tension and went along two paths and pulled something along two paths, again, that work is going to depend on which path I take. So I cannot assign a an energy, or sorry, I cannot assign a potential energy associated with those forces. In upper division mechanics classes, we have mathematical ways of proving that forces are conservative or non-conservative, but it all boils down to the same thing. Forces can only depend on position, and they have to be path independent. So what we've got now is we can kind of sort of think about all the forces that are acting on our system, and we've got conservative forces that we can apply potential energies to, and we've got non-conservative forces, ones that we can't. Of those non-conservative forces, generally what we're going to want to do is split them up into dissipative forces, forces like friction, where it's creating changes in thermal energy, and all the other forces that are non-conservative, like say a tension, we would want to think of as external forces to our system. And if we do that, we can analyze everything in our system and get a nice clean picture of our energy model. So if we think about it, we're going to start with Newton's second law. F net is equal to mass times acceleration. And if you recall, what we did at the very start of our energy section is we did some calculus where our acceleration is the derivative of velocity with respect to time, and we can apply sort of a chain rule to that and do a dv dx, dx dt. And we've just done some calculus on Newton's second law, right? Now, so we have F net, I'll just rewrite this here for clarity, is equal to m. The dx dt is just our velocity, so mv dv dx is what Newton's second law after some calculus gives us. Now, we just mentioned splitting our forces into conservative plus non-conservative forces, and that non-conservative forces are going to be dissipative and external forces. We can split those up into that way. So our net force is just going to be the conservative forces plus the dissipative forces plus the external forces. And that net force is going to be mv dv dx, right? And then what we can do is we can bring the dx over to this side and do our integral from our initial position to our final position of Fc plus F dissipative plus F external dx is equal to the integral from V initial to V final of mv dv. And this may seem really familiar to you. This is what we did at the start. This ends up being 1/2 mv final squared minus 1/2 mv initial squared. So this is our change in kinetic energy of our object. And if we split this up into three integrals, we have an integral from x initial to x final of Fc dx plus an integral from x initial to x final of F dissipative dx plus the integral of F external dx from x initial to x final. And we've defined each one of these terms, right? These, the integral of the force with respect to distance was just work, but for our conservative forces, this, we defined change in potential energy as negative the work done by those forces. Turns out that's the work done by conservative forces. So this is our work done by our conservative forces, and it's equal to negative the change in potential energy. This dissipative force, this is, that change in thermal energy that we defined was essentially negative the work done by a dissipative force, right? It was that force of, if you recall, we used it for friction, and it was Fk times delta x, which was negative the work done by that dissipative force. So this is going to be negative delta E thermal. And lastly, the external forces, these are the forces that are applied from outside our system. This is just the work done by those external forces, right? And all of this is equal to delta, the change in kinetic energy. What this allows me to do is bring all the changes in energy to one side, and I have the equation that is our sort of full energy model. The work done by the external forces causes a change in the potential kinetic and thermal energies of our system, right? So external forces causes a change in the total energy of our system, right? Sorry, delta for change. Another thing we want to define is the potential plus kinetic we can think of as the mechanical energy. This is something we call the total mechanical energy of the system. And then the thermal energy is that microscopic sort of energy in our system. And if we put them together, we get the total energy in our system. But you can sort of hopefully see now how Newton's second law leads to this energy model that we've sort of derived down here for our system. And that's really what we're doing. We're going to be looking at our system, thinking hard about what type of forces are involved and how we can define our system appropriately. And then it's a matter of just bookkeeping where the energy in our system is, right? So if we look at putting this all together and looking at that, we have we define our system as, whatever this box, earth, and spring. We can look at the forces, think about our kinetic and potential energy, or our mechanical energies in our system, as well as the thermal energy. Those energies can change back and forth, but unless there's some external force acting on our system, that total energy isn't going to change. And hopefully after spending, a couple weeks and doing some problems and all our synchronous sessions, we're getting comfortable with this. It's really, I like to think of it as just bookkeeping where the energy in our system is. Has our kinetic energy gone up? Our potential energy changed at all? Is there some external work that's adding energy to our system, etc.? And again, we'll do some examples in class in our synchronous sessions and that. But if you have any questions, feel free to email me. We'll discuss this a lot more, but hopefully it's starting to come together.